Let's do a second example where we can get a flavor for what happens when perhaps it converges absolutely. So here we have sum k equals 1 to infinity minus 1 to the k times k squared over 2 to the k. And so again, we're going to do step 1, the divergence test. The limit of this as k goes to infinity, right, we have k squared over 2 to the k. Either we remember that k squared grows more slowly than this exponential 2 to the k, or else we use L'Hopital's rule to figure this out. In either way, we get a limit of 0. So it's inconclusive. And honestly, at this stage, if the limit is something that is delicate to figure out, sometimes you can go on ahead and go on and go forward and just go ahead and use the test that you want in step 2. Right, so in step 2, we look at what we get by taking the absolute values of these terms. So that series, k squared over 2 to the k, we want to use some test on it. And here I'm going to say, let's look at this, and it looks an awful lot like a geometric series except for this k squared term. So the idea would be to use a ratio test or a root test. So let's do the ratio test. And we look at this limit as k goes to infinity of the ratio of two subsequent terms. So that's going to be k plus 1 squared divided by 2 to the k plus 1. Right? That's the k plus first term in that series. And then we're going to get 2 to the k over k squared as we multiply by the reciprocal of the kth term of our series. Okay, so now let's calculate this limit. We get, putting the k plus 1 squared term over the k squared term, we get k plus 1 over k whole thing squared. And then combining the powers of 2, we're going to get 1/2. Now, as k goes to infinity, k plus 1 over k is going to go to 1. So this whole thing in here is going to go to 1 squared. So that limit is 1/2, which is less than 1. So that series, right, so the series of absolute values, converges. We can stop now in our procedure. Right, our procedure, once we get a positive result, we stop. So this means that our series converges absolutely.